Let's solve this problem drawn from the International Mathematical Olympiad. Specifically, we would like to calculate the three unknowns x, y, and z, and understand what are the conditions under which, specifically, what are the real numbers a and b, under which those three unknowns x, y, and z are distinct and positive real numbers. Well, I would like to start basically from the first equation. Specifically, here, as we can see, that there are three squares: x squared, y squared, and z squared. And here, the first equation involves the same structure, basically. So I would suggest that we calculate the square of this trinomial: x squared plus y squared plus z squared plus 2xy plus 2xz plus 2yz. It is equal, well, a squared. Once we have this, well, we can insert into the second equations. So what we have here, we just recast this equation as this a squared, and then we bring all those guys on the other side. So we have a squared minus 2xy minus 2xz minus 2yz, and this is well. Now we can insert this into the second equations, and what we obtain, we basically obtain the following situation: a squared minus 2xy minus 2xz minus 2yz, it is equal to b squared. This leads to what? We have z, and we can solve this equation for z. This means that 2xz plus 2yz, it is equal. This guy goes to the left hand side, and we obtain a squared minus b squared minus 2xy, which is basically to say that a squared minus b squared z squared. Now, this implies what? Look at here, the left hand side. We can recast this as follows: 2 multiplied x plus y z equal, and this we keep it the same, square minus b squared minus 2z squared. And according to the first equation, basically what follows? It follows that this guy in here, it is equal to a minus z. Now, what does this imply? Well, this implies the following. You can write right here. Imply that 2az minus 2z squared equal a squared minus b squared minus 2z squared. And this is a good news, because we can delete this, and we can solve it for z. Frame it. So basically we have found the first solution. So to identify under what condition z, x, and y are three positive and distinct solutions for every real values of a and b, we notice that the first equations, and I show here again, the first equations implies what? That a must be larger than 0, it must be positive 2. We come to the conclusion that two important conditions are: first, a must be positive, and according to this condition, the denominator here must be positive. In order for z to be positive, the numerator must be positive. This implies that the second condition is that a squared minus b squared be larger than be a positive number. So we have found those two conditions, and now let's use the first equation and the third. I show again, it's a little bit complicated. The first equation and the third equation to solve for y. We rewrite x as what? As a minus y minus z. This implies that a y minus y squared minus z y equal z squared. Again, this what implies now this is a quadratic equation, and if we want y to be distinct solution, we have to impose that the discriminant to be larger than 0. In other words, we have to impose that the delta is positive. Now, what is the delta? So we have to calculate delta. It is nothing but we have minus 3a power 4 minus 3b 4 plus 10a squared b squared. So in this case, what we need, it is to add a4 minus a4 plus b raised to the power of 4th minus b raised to the power of 4th, and then again 4a squared positive. So in this case, as you can see, I don't know if it is clear, the pattern here, the pattern involves this guy in here and this guy in here, b and 8. Okay, well, in this case, we have to consider probably the second condition. Yes, as we said, we found those two conditions. A must be positive, and then we need to have a squared larger than b squared. What does this imply? Well, implies that we don't need to use modulus here when we use the square root of the left and right hand side, because as you can see, this is, of course, this is positive. So in this case, we can calculate the square root, and we have this situation, a squared minus 2b squared. This in turn implies this situation. It means well, minus 2, it becomes plus 3b squared, 3b squared larger than a squared. So 3b squared larger than a squared. So in summary, what we have, what we found out that this leads to a. We don't need to use the modulus. Why not? Because a, it is positive. So we can write it this way, and when we calculate the square root of this, this requires the use of modulus, and this can be written this way. So this is a more concise way of combining these two conditions. For the sake of completeness, let's calculate the third unknown, and the third unknown it's x, and we do it by using our knowledge about the unknown y. So we can use the first equation. We can use this. Oops, it's not visible. We can use this equation, and we can use it the following way. So, which basically has pretty the same structure as y. So for the sake of clarity, I just write it again. What about z? In this case, we know that z, it is z square root of xy. This is nothing but the geometric mean, and we know that provided that x and y are not the same, then this is always less or equal than the arithmetic mean, x plus y over 2. The geometric mean basically is always less than the arithmetic mean, unless, in this case, well, x equal y, in which case basically we would have x, y equal z. The geometric mean is a real number between x, in this case x and y, so it is like x, y, it is also distinct under these conditions, and this ends our proof.